Hi folks, welcome to part 2 of the tutorial on properties of rational exponents, which goes with section 7.2 in your textbook. Where the previous video left off was right here. We were writing radicals in simplest form, and we were breaking down these cube root of 54, the fourth root of 80, and really the next part of this video picks up right from there. And we're going to actually try to add in or subtract radicals, but first we need to talk about like radicals or like terms. So we say that two expressions are like terms or like radicals. They need to have the same index, which means if one's cube rooting, the other one has to be cube rooting or fifth rooting on both of them or seventh rooting. And they need to have the same radicand. So what we're taking the root of needs to be the same. This is actually the same property that we've had before. Something like 3x plus 4x squared. These don't have the same exponents. These don't have the same radicals, if you will. What's being raised to the power, those are the same, but those exponents weren't the same thing. Likewise, we couldn't add together 3x squared plus 2y squared. We can't do that because our bases are different. Our radicands are different. So some examples of radicals that are like terms is something like the cube root of 7 and maybe 11 cube roots of 7. Right? So we can add 1 cube root of 7 with 11 cube roots of 7 and get 12 of them. Or we can have something like a fifth root of, let's say, 25x. And we can have 6 fifth roots of 25x. Those would be like radicals as well. Again, their indices are the same, the radicands are the same, and so we say that they're like radicals. So let's see what we can do with this and what we can't do with this. If we have like terms, we can combine them, right? And we saw from previously that if we have different bases, that we can't combine these. So I can't combine this first set here, right? Because we have a 3x and a 2y. Well, those aren't like terms. And we should also know that we can't combine 3x and 2x squared, right? Those are not like terms, right? Because our exponents are different. Let's go down to C, and we're going to see some maybe some unexpected stuff as we move through this list here. The square root of 4 plus the square root of 9. Well, as is, we cannot add these together and get the square root of 13. Let's see why this doesn't work. The square root of 4 is 2. The square root of 9 is 3. So this should equal 5. Well, does 5 equal the square root of 13? Well, no. It's not really even all that close. So this doesn't work. We can't just add our radicands together and leave it under the square root. So you either need to simplify them like I did here, or they really just need to be left alone. So let's look at D. Well, our radicands are the same, both 8s, but we're taking different roots, right? We have a third root and we have a square root. Well, those aren't like terms. Those cannot be added together. Okay, on to E and F. Let's see. E, well, it looks like something good is happening here. We have 11th roots. Excuse me, we're taking the radicands are the same. They're both 11. And indices are the same. Both of these are 5. So it looks like they're both, they're like terms. So we can add these together. I have 7 fifth roots of 11 plus 3 fifths roots of 11. I get 10 fifth roots of 11. Okay, last one, and we'll move on to something new here. Do these look like they're like radicals? Well, at first glance, no. I do have the same indices out here, both 3s, but the radicands are different. However, there is something we can do with the cube root of 16. Yeah, we can simplify, can't we? Okay, here's a little hint before we actually go ahead and simplify this. If these are going to be like terms, then what does one of these factors need to be? Well, the hint actually comes from over here, from the other part of the question. So we sure can, I can just go ahead and simplify this as I normally would, but I should know, or I should maybe take a guess, that the non-perfect cube is going to be a cube root of 2, That way it matches up with what I had over here. So anyways, the other factor, 2 times what gives me 16? Well, that's going to be 8. So I can say that the first factor needed to be the cube root of 8. And now I can rewrite all this stuff as, well, 4 times, I have a cube root of 8, which, by the way, the cube root of 8 is 2, right? So the cube root of 8 times the cube root of 2 times this original cube root, plus this original cube root of 2. So I'm just going to do a little multiplying here. I'm going to get 8 cube roots of 2 plus 1 cube root of 2. And I'm going to get 9 cube roots of 2 out of this. So again, as it turned out, I can't actually combine these. I just needed to recognize that that term right there, that cube root of 16, was not simplified. And I can go ahead and actually complete the problem. Okay, moving on. So at this point now, we're going to take a little more time and simplify expressions with variables. So let's first talk about, and we'll see why this is not simplified. So I can rewrite this as the cube root of, well, 125 is 5 cubed. And I wrote it like that because I want to write this as something being cubed because I want to take the cube root of it. So if I just look at my numbers, I'm not going to deal with the y's first. I'm just going to deal with the 5 cubed root, the 125. Well, the whole idea of writing this as 5 cubed was that I'm going to unwrap it by taking the cube root out here. So what's the cube root of 5 cubed? Well, those operations unwrap each other, and I get back just 5. Okay, now we're going to look at what's happening with my y to the 6th. Well, again, I want to write this as something cubed. So, what can I do with y? I need to rewrite this so that y to the 6th equals something cubed. Well, the base would then need to be y to the 2, right? Because 2 times 3 is going to give me 6. So when I take my y squared, I cube it, and I take the cube roots, I get back what I started with, which was y squared. Now, if that was a little convoluted, let me show you a little different way of doing this. And it might be a lot easier here. Again, I'm going to look just at the y's with this. I'm going to disregard the 125. I'm going to rewrite this as in exponent form. So that means I can rewrite this as y to the 6 over 3. And there's your y squared. So if you look at what I did here, I just divided the 6 by the 3, and I got y squared. And I'm done with that factor, at least in this problem. Okay, let's look at some more examples and see if these get any nicer, if they get any worse, or if they just stay the same. Okay, so looks like I'm going to do a square root out here of 9u v to the 10th. Hold on 1 second. Okay, sorry about that. So, anyways, we were going to take care of this square rooting issue that we had out here. I'm not even going to change this to radical form. I'm just going to distribute this power to all my stuff here. So I'm going to raise 9 to the 1/2. Well, that just means square root of 9 is 3. I'm going to have u squared, right? U squared to the 1/2, or in other words, 2 times a half is going to be 1. So I'm going to get u to the 1 there. And I'm going to have v to the 10th to the 1/2. Again, I'm going to multiply those exponents and get v to the 5th. And that's really just a nice kind of a simple one there with some exponent properties. Anyways, let's move on to some that have a little more teeth to them. So we're going to take the 4th root of x to the 4th over y to the 8th. Again, when I have a fraction here in my radical or with exponents in general, I'm really going to treat this as 2 separate problems. I'm going to do not the 3rd root, I'm going to do the 4th root of x to the 4th, and that's over the 4th root of y to the 8th. And I'm going to use that idea that we just did before of rewriting this in exponent form, where I write this as, there's my numerator, and my index is my denominator. So this is going to be x to the 4 over 4, or x to the 1, over y to the 8 over 4, or y to the 2. And I end up with something nice like x over y squared. for my solutions. Okay, so let's move on. We're going to skip this last one there, we've already seen plenty of problems like that already. So we'll do one last little bit here, and then this will be the end of this video. We're going to really just more of the same. We're going to write variable expressions in the simplest form here. And again, I'm going to employ that technique that I used before with the exponent and the index, with the division there, to help me simplify these really in a quick fashion. So what's important about this is we really recognize that this is really four problems here in one. We're dealing with the 7, my coefficients, that's one issue. Then I'm dealing with my A's, then my B's, and then my C's. And there's no need to mix those things up. So if you can, or if it makes sense, try to ignore the A, B, and C for now, and we'll just deal with the coefficient. So the 4th root of 7, there's nothing I can do with that. So I'm going to end up with just the 4th root of 7 inside there. All right, now I'm going to move down to my A's. Okay, well, this is A to the 4th, and then I'm taking the 4th root. Well, again, those are going to unwrap each other, right? We're raising something to the 4th and then taking the 4th root. We should get back what we started with, which is A. If you don't like that explanation, then you can just change it to exponent form as 4 over 4, and we get A to the first either way. So in my answer over here, I'm going to put A outside the radical, right? So it's A to the 1. I don't want it inside the radical, otherwise it's A to the 1/4. And then I'm going to move right down my list. I'm going to work on my B's, then my C's, and then I'll be done here. So I look at B to the 12th. Again, I'm just going to divide 12 by 4 and get B cubed. And that belongs outside, right? Because again, it's not in the radical. I'm going to need a little space here for my C's in a moment. Okay, so moving on to the C's. Well, I want to divide 11 by 4. Well, this one's not quite as nice because 4 does not go in evenly into 11. But how many times does it go in? Well, if I do 11 divided by 4, that goes in twice with the remainder of 3, right? Okay, so here's how we treat this. I bring out a C to the 2 outside the radical, and then inside the radical, I had to leave 3 of those C's behind. So it really looked like this. When I was doing the 4th root of C to the 11th, if I was able to change that into a C to the 4 times C to the 4, there's 8 C's in there, and then we only have 3 more left over to get up to C to the 11th. So 2 of those factors came out, right? 1, 2, and we got C to the 2 when it came out, and that last C cubed was left inside, and that just stayed in there. And that's what our final answer looks like there. 8b cubed c squared times the 4th root of 7c cubed. As ugly as that is, that's what we get there. All right, let's look at one more of these. So we're going to do the cube root of 16x over y to the 7th. So again, I'm gonna break this up into 3 different thoughts: my 16, my number, my coefficient, my x's, and then my y's. Well, we already did the cube root of 16 earlier, right? We said this is the cube root of 8 times the cube root of 2. So the cube root of 8 is 2 times the cube root of 2. So when I go to write my solution over here, I'm going to have a 2 on the outside, and I'm going to have inside the cube root, I'm going to have a 2. I might have other stuff inside and other stuff outside, but I definitely have that to begin with. And now I'm going to go ahead and fill in my x's and my y's. Okay, with my x's, well, I have an x to the 1 inside, and it's in the numerator, it's fine. There's nothing I can really do to simplify it, so I'm really just going to carry that through. It's really the y's that are going to give me the most trouble, and we'll see why here right now. So what do we have here? Well, we have the cube roots. Again, I'm blocking out everything else of 1 over y to the 7th. Well, it would be nice, it wouldn't be so bad if that number was divisible by 3. If that was, let's say, a 9, I could say, okay, this is going to be the cube roots of 1 over y to the ninth, and I can just do that as the cube root of 1 is 1, and then 9 divided by 3 is 3, and get y cubed in the denominator. I can write that up here, and really be done with the problem. It'd be nice and simplified. But that's not really the case, right? It's really y to the 7th, and I need to adjust accordingly here. So here's what I'm going to do. I'm going to, I want to make that y to the, as it turns out, the 9th. And the reason why is, or the way I'm going to do that is I'm going to multiply by y to the 2 down there, so that way when I add these two together, I get y to the 9th. Okay, to do that properly, I actually need to multiply by y squared over y squared, right? I'm really multiplying by 1 inside that radical. So that when I go ahead and simplify this, I get the cube root of y squared in the numerator, and in the denominator, hold on, let me just fix my 3, we get y to the 9th, but it was the cube root of that, so it's really y to the 3rd down there. So I can go back up to my final answer up here and say, okay, I end up with y cubed in the denominator, and I have this y squared that's inside the cube root, so I'll put it up there, and then be done with the problem, and then be done with the problem. So this last one here is definitely a bit trickier. You might want to watch this one again and see if it helps out at all. It's one of those things where it's a skill for us. It's not the end of the world if we don't nail this perfectly, because it's really just helps us to clean up problems more than anything else.